So welcome back to lesson 8.4, parametric equations. So I have two more examples for eliminating the parameter and finding a parametric equation with given information. So in this one, we're going to do a harder example for eliminating the parameter. So they've given us that x equals sine t and y equals 2 minus cosine squared t. Now, in this one, I'm actually going to start off with the harder equation because x equals sine t, there's no easy way to solve for t. I could do an inverse sine on both sides, but that's not really going to help much because then I'll get cosine squared of inverse sine x. So that's not going to help much. So I'm going to play around with this one because I see a cosine squared. And that makes me think of something that we learned last chapter. Okay, we know that sine squared plus cosine squared equals 1. So what I can do is solve for cosine squared and get cosine squared equals 1 minus sine squared. And I can take this and replace the cosine squared up here. So I'm going to do that. This way, both of my equations are in terms of sine. So I'm going to get y equals 2 minus 1 minus sine squared t. Now I'm going to simplify that. So I get y equals 2 minus 1 is just 1 minus sine squared t. Now notice x is sine t. So this I can replace with an x squared. So I get y equals 1 minus x squared. And I've eliminated that parameter. So you are allowed to use your trig identities that we learned when we did trig functions. Now, another thing to note is that they ask us to graph this. So if you want to, you can graph it from these. Pick values for t and put them in. Now you're allowed to pick any values for t that you want. So you can do any values. It could be 0, pi over 4, pi over 2, any values you want. So I'm going to get out my unit circle. Here it is. Okay, and I'm going to do x equals sine t squared. Sorry, x equals sine t and y equals 2 minus cosine squared t. Notice what happens. At 0, x is just the sine value of 0, and y is cosine squared, which is 1, and 2 minus 1, which is just 1. Okay, I can do pi over 2, I can do pi over 4. I get to pick what I do. So if I do pi over 4, x is square root 2 over 2. That's just the sine value there. And from my calculator, I find out that the square root of 2 divided by 2 happens to be about 0.7. And y is this thing squared. When you square this thing, it actually reduces to 1/2. And 2 minus 1/2, which is 1.5. When t is pi over 2, sine is 1 and cosine is 2. And I would just keep going with this, but let me show you what we're going to get with that. I'm just going to sketch the graph. We have the point 0, 1. We have the point 0.7, 1.5. And we have the point 1, 2. Now, when I go on to 3 pi over 4, and again, you can pick any ones that you want. Watch what happens. My x value is going to be the sine, which is 0.7 again. And my y value, I'm going to square the cosine, which becomes 1/2. And then I have 2 minus 1/2. I'm back at 1.5. So what I did is I went this way, and now I'm going back in this direction. And then I'm going to go back this way, and guess what? I'm going to have a point here, and it's going to bounce back and forth between these 2 points. okay, between the point 1, 2 and the point -1, 2. And you'll see that a lot of times with sine and cosine functions, it'll do that. It goes in one direction and then it bounces back and goes in the other direction. The other thing that might happen with sine and cosine functions is that it might actually create a circular function or an oval where it's consistently going around the oval. It just makes a circle like this. Okay, so that's how you deal with eliminating the parameter when you have sines and cosines involved. Now let's look at linear functions. Okay, so what they've done is they've given me information about a linear function, and they want us to find the parametric equation for this. Okay, so they told me a slope, and they told me a point. What I'm going to do is I'm going to use this to create my parametric equations. Now the slope is rise, or the y values, over the x values. So the change in y over the change in x, rise over run. So when my slope is 3, I can write that as a fraction as 3 over 1. So the change in y is 3, and the change in x is 1. So for each space I go, my y has to change by 3, and my x has to change by 1. Now notice in my point, this 2 refers to an x value, a starting position for my x values, and this 6 is a y value, the starting position for my y's. So if I want to describe what's happening with my x's, I can write x equals my starting position plus 1 times my parameter. Okay, because this is how much x is changing by for each parameter. And remember, for each means multiplying. Okay, for my y's, I'm going to get my starting position from my point. It's a 6. And I'm going to add on the change in the y, 3t. Okay, so these are my parametric equations that model this linear function. Now, if I want to check my answer, I can simply eliminate the parameter. Now, it's up to you how you do that. I'm going to solve in my x equation for t, because all I would have to do is subtract 2. So to check my work, let me do it in red so you guys can tell that this was checking. This is the actual final answer. This is it. Okay, but if you wanted to check it, I would subtract 2 here to get t equals x minus 2. Then I would take this and put it into the y equation. So I have y equals 6 plus 3 times x minus 2. Okay, I'll distribute my 3. And I'll combine my like terms. And now this should match up with what I know about this. It does have a slope of 3. And if I put in 2 for x, I do get 6. Okay, so this point is true and it has the slope it needs. So I've checked my work now by eliminating the parameter. But the actual answer that I needed was this one right here. Okay, so we have one more video for you. So come back for that one and let me know if you have any questions about this.